We are going to begin this example by yet again making a table for each of the three pieces of this function. So we're going to make a table for the first piece. The first piece is for x values that are less than 0, and the y value that comes out is always -1. It is a constant piece, so no matter what x values we plug in, we're only going to get out -1 as our y value. We will begin by first plugging in 0, even though 0 is not included in the first piece because it says x is less than 0. That means that we will have an open point at the point 0, -1. I'll choose some more x values that are less than 0, like say -1, and I'll just choose -4. So we have the point -1, -1 that is closed, and we have the point -4, -1 that is also closed. I'll go ahead and plot those points. So here's the point 0, -1 that is open, here's -1, -1 that is closed, and here's -4, -1 that is closed. I will connect those points and continue on with an arrow because that piece continues for all x values that are less than 0. The second piece of the function is for x values that are between 0 and 2, and it includes 0 and 2, and we get out x minus 1. We need to make sure that we put both endpoints of 0 first, because it is the first endpoint, and 2 last, because it is the last endpoint in our function. We can choose any number as the third point as long as it is between 0 and 2. So typically whenever we're graphing a piecewise function, I will ask that you make a table for each piece of the function and use at least 3 x values in that table, in each table. So I'm going to choose 1 because 1 is between 0 and 2. When I plug in 0, we get out 0 minus 1, which is -1. When we plug in 1, we get out 1 minus 1, which is 0. And when we plug in 2, we get out 2 minus 1, which is 1. I'm going to specify whether my endpoints are open or closed. Both of these inequalities are including 0 and including 2 because of the or equal to. So that's what's telling me that this is closed. I'm just going to put a CL for closed. The fact that these are or equal to, the fact that those inequalities are underlined tells me that it's closed. In the first example, that was not underlined, and so that told us open. So let's go ahead and plot the points for that middle piece that only exists between 0 and 2. We have the point 0, -1 closed. Notice that does close in this point right here at 0, -1, and that is okay. We have the point 1, 0, and then we have the point 2, 1. And I'm going to connect those 3 points. Notice that I am not using an arrow for that second piece. There's no arrow on that piece because that piece stays bounded between 0 and 2. The first piece did have an arrow, and that arrow went off to the left because that piece continues for all x values that are less than 0. Now let's go look at our table for the third piece for x values that are bigger than 2, where we plug in -2x plus 6. We will first plug in 2. Even though 2 is not included in that piece, we need to make sure that we plug 2 in first. And then I'll choose 2 more x values that are greater than 2, like 3 and 4. When we plug in 2, we get out -4 plus 6, which is 2. When we plug in 3, we get out 0. And when we plug in 4, we get out -2. So just a quick recap, where am I getting these values from? For instance, -2, I'm plugging in the x value of 4 into this x right here to give me -2 times 4 plus 6, which is -8 plus 6, which is -2. So now I'm going to plot these points, and I will specify that the point 2, 2 is open because this inequality does not include 2. So we have an open point at 2, 2, we have the closed point 3, 0, and then we have the closed point 4, -2. I'm going to connect those pieces. But this third piece does have an arrow, and it has an arrow that goes off to the right because this piece exists for all x values that are greater than 2. So for example, we could have plugged 6 into this function, and we would have gotten out -2 times 6 plus 6, which is a -6. So if I would have plugged in 6, I would have gotten a point way down here. So this piece continues on forever. Generally speaking, when you look at your inequalities, so I'm talking about these 3 things here, if the inequality only has one number, there will be an arrow. If the inequality has two numbers, like in number 2, the purple piece, then there's going to be no arrow because that piece is going to stay between those two x values. So there is the graph of our function. I can see from the graph that the domain is all real numbers. Some people may wonder, well, you have an open circle there at 2, but we also have a closed circle there at 2, so that is definitely included in our domain. The range runs from the bottom going down from negative infinity because this pink piece does not stop. It goes on forever. And the highest point on the function, the highest y value we see is the y value of 2 that is not included. So we have a parenthesis on that piece there. It is in fact just a coincidence that this range is the same as the range from our last function. Now let's go on to find our intercepts algebraically. I will begin with the y-intercept. We find the y-intercept by plugging in x is equal to 0. We have to first figure out which piece of the function we want to use. So which of these three inequalities is 0 valid for? 0 is only valid for the second inequality because it says x is greater than or equal to 0. So we're going to plug 0 into the second piece, which we have already done. We did it right here and we got out -1. Because 0 minus 1 is -1. So we do have an algebraic y-intercept of 0, -1. We can see that we found it on the graph right there. To find the x-intercept, we need to set all three of the pieces equal to 0. If we try to set the first piece equal to 0, so first let me draw a line here, x-intercept. If we try to set the first piece equal to 0, we would be setting -1 equal to 0, which is simply not true. So the first piece gives us no x-intercept, which we can see from the graph, right? That blue piece, the first piece, it never touches the x-axis. It's always constant. I erased it. It's always constant at -1. Now let's go on and set the second piece of x minus 1 equal to 0. Quickly add 1 to both sides to get that x is equal to 1. Before we can definitely say that 1, 0 is an x-intercept, we have to see, does the second piece even exist when x is 1? Does 1 satisfy the inequality for the second piece? And it does, because 1 is in between 0 and 2. So we do have an x-intercept at 1, 0, and we can see that on the graph right there. Now let's go on and set the third piece of -2x plus 6 equal to 0. I'm going to add 2x to both sides of this equation to get that 6 is equal to 2x, and then I'll divide both sides by 2 to get that x is equal to 3. We then have to check, does 3 satisfy the third inequality? The third inequality is only valid for x values that are bigger than 2. And 3 is bigger than 2, so we do have a second x-intercept at 3, 0, which we can see on the graph. So again, when you're finding your x-intercepts for a piecewise function, you need to set all three pieces equal to 0, and then check, does your solution fit the piece of the inequality that you were given?